In recent years, China has rapidly emerged as the global leader in lunar exploration. While most of the world has focused on Mars, Chinese missions have been systematically targeting the Moon, specifically regions no human or machine had previously studied. Their robotic landers and rovers have accessed the far side of the Moon, returned with geological samples, and revealed significant new information about the Moon's formation, composition, and potential for future use. Let's examine what they found and what it means. The Moon is tidally locked, which means we always see the same face from Earth. The far side is perpetually hidden from us, and until recently, unexplored. In January 2019, China's Chang'e 4 mission became the first to land on the lunar far side, specifically in the von Karman crater within the South Pole Aitken Basin, one of the oldest and deepest impact structures in the solar system, measuring approximately 2,500 kilometers wide and 13 kilometers deep. Aboard the lander was the Yutu-2 rover, which began exploring this impact zone. The scientific rationale was clear. Such a deep basin likely exposed material from the Moon's mantle, a region between the crust and core that had never been sampled before, and that's exactly what they found. Preliminary analysis suggests that some of the rocks collected by Yutu-2 originated from the mantle, marking the first time such material has been accessible for study. This discovery has direct implications for the prevailing theory of the Moon's origin. The giant impact hypothesis, sometimes called the Big Splash model, suggests that about 4.5 billion years ago, a Mars-sized body collided with Earth. The resulting debris eventually coalesced into the Moon. Computer simulations have shown that this scenario best explains the isotopic similarities between Earth and Moon rocks. However, it also predicts that the Moon, being smaller, should have cooled much faster than Earth. But Chinese findings suggest otherwise. In 2024, the Chang'e 6 mission returned samples from the far side's South Pole Aitken Basin. Laboratory analysis revealed rocks that challenge assumptions about the Moon's thermal history. Some of the volcanic material collected was only 2.8 billion years old, significantly younger than the average 3.5 billion-year-old rocks collected during NASA's Apollo missions. Yet in the same region, a fragment of lava was dated to 4.2 billion years ago, making it the oldest known volcanic rock from the Moon to date. This wide age range suggests that lunar volcanic activity persisted much longer than expected, possibly spanning over 1.4 billion years. That longevity contradicts the idea that the Moon became geologically inactive early in its history. Even on the near side, China has contributed new data. The Chang'e 5 mission in 2020 landed near the Rumker Dome, a volcanic formation in the Oceanus Procellarum region. The site was chosen due to its geological diversity and evidence of recent volcanic activity. Chang'e 5 returned around 1.7 kilograms of lunar samples, including basaltic rock dated to around 2 billion years old. These were the youngest lunar rocks ever returned to Earth. This contradicts earlier expectations that significant volcanic activity ended over 3 billion years ago, and it indicates localized heating in the Moon's mantle continued for far longer. One of the most notable scientific findings from the Chang'e missions was the discovery of a new lunar mineral, named Chang'e by Chinese researchers. This mineral is transparent, crystalline, and notable for containing trace amounts of helium-3, a rare isotope not naturally abundant on Earth. Helium-3 is produced by the solar wind and accumulates on the Moon's surface due to the absence of a global magnetic field. On Earth, our magnetic field deflects the solar wind, preventing helium-3 deposition. The reason this element is significant is its potential role in nuclear fusion. While helium-3 fusion reactors do not yet exist, this isotope has properties that make it attractive for future energy systems. It produces no radioactive byproducts, emits minimal neutron radiation, and has a high energy yield per unit mass. Helium-3 fusion has been researched since the 1980s, and while challenges remain, including the development of viable fusion reactors and helium-3 extraction techniques, the Moon is considered a potential long-term supply. Another critical breakthrough came from the detection of water molecules, specifically H2O. Water was found within a hydrated salt mineral in samples from the Rumker region, suggesting it was chemically bound within the rock. This was the first time a complete water molecule had been identified in returned lunar soil, and it implies that water may be more widely distributed across the moon than previously believed, not just in permanently shadowed craters near the poles. This discovery could impact the viability of in situ resource utilization strategies. Water can be split into hydrogen and oxygen, offering potential for life support systems, fuel production, and habitat construction on the lunar surface. China's methodical approach contrasts with the Apollo missions, which prioritize speed and human presence. Apollo missions explored limited areas near the equator and focused on returning samples rather than performing broad geological surveys. In contrast, China's Chang'e program targets geologically diverse locations and prioritizes automated sample collection, remote sensing, and detailed stratigraphy. Each new dataset contributes to a growing lunar geological database, with implications for both planetary science and future human colonization efforts. The long-term vision is clear. China is not only studying the moon's past, they are preparing for its future. Plans for a permanent lunar research station by the 2030s, potentially in partnership with other nations, have already been proposed. From mantle-derived rocks to helium-3 and lunar water, China's robotic exploration is reshaping our understanding of the moon. With each mission, they're not just uncovering ancient history, they're building the foundation for permanent lunar presence. And right now, they're doing it faster and more comprehensively than anyone else. If you found this breakdown useful, consider subscribing for more data-driven analysis on space, AI, and emerging tech. Thanks for watching, and I'll see you in the next one.